Imagine you get in a time machine and go back to the 1960s. Here, you end up in a live audience of a show called Let's Make a Deal. The host, Monty Hall, singles you out and asks you to participate in the chance of a lifetime. You're presented with three doors. Behind one of the doors, a heaping pile of money, let's say $1,000,000. And behind the other two, goats.
Monty asks you to pick one of the doors, informing you that you will get to keep whatever is behind it.
Let's say, for the sake of this problem, you select door number 1. Before you get to open the door, Monty opens one of the other doors, let's say door number 2, to reveal a goat. He says something along the lines of, well, good thing you didn't pick door number 2, or you'd have a new, loud, and smelly roommate.
But before we open your door, I'll offer you a chance to switch your door to door number 3. One contains the other goat, but one contains $1,000,000. I encourage you to pause the video to consider your $1,000,000 decision. Alright, so you made your decision. Now, before we proceed with the game, I want you to reflect on what decision you made, why you made it, and whether or not it actually matters from a probability standpoint. If you're watching this with others, I encourage you to discuss these questions before continuing. Alright, so you've either decided to switch or stick with your guns. I'll tell you right now that if you decided to switch doors, you've made the right choice. By switching, you just improved your odds of becoming a millionaire by 33.3 repeating percent. Well, hold up, that can't be right. After Monty opens a goat, there are only two doors left. One has a goat, and one has the money. Wouldn't it be a 50-50? A coin toss? Well, if you find yourself thinking this, you've just fallen for a mathematical illusion.
Don't worry though, many contestants from the show fell for the same illusion and chose to trust their gut and stick with their initial choice. Let's prove that this is a bad idea by looking at the concept called probability space. Probability space is a mathematical model that assigns a likelihood to each element in a set of all possible outcomes of a given event. In the case of the Monty Hall problem, let's first look at the instance where you do not want to switch. It's pretty obvious that in this case you have a 1/3 chance of winning, since your decision is left up to random chance. The first key point to notice is that you will most likely choose a goat on your first guess. Once you choose a door, Monty opens one of the other doors. And the second key point to notice is that Monty always opens a door with a goat. Now there are two doors left, one with a goat and one with the money. If you keep both of these points in mind, it becomes apparent that since your initial guess is probably a goat, it stands to reason that the other door probably has the money. It's a 66% repeating chance, in fact, that the money will be yours if you switch. So by thinking about the problem in terms of probability space, that is breaking it down into all possible outcomes, we were able to turn a seemingly random choice into a well-informed one that allows us to walk away with the money 2/3 of the time. To see an intuitive visual breakdown in the probability space for this problem, we encourage you to check out the handout provided.
This may seem like an arbitrary problem about fake goats, fake money, and a game show that you'll probably never appear on, but the process of using probability as a tool to make better decisions is a very real skill that you can master. It will give you a competitive edge in board and card games, but also in the real world. Anywhere there is uncertainty or randomness, there is opportunity to better understand the probability of certain outcomes. From the likelihood of rain to the likelihood of the opposing batter getting a home run, you have the power to use the numbers to your advantage. Just make sure you use your powers for good.